Great. So I'm Marcus Quigley. I'm with Geosyntec Consultants out of our Brookline, Massachusetts office. And hopefully, I know that I've been given 40 minutes, so I really appreciate that. Hopefully, you'll walk away as excited as I am about the work that we're doing. This is by far the most interesting thing that I've gotten to do in my career. Certainly, we haven't done it alone. We have a whole bunch of collaborators. Probably the most important folks that have really worked with us on this work are WRF. They have funded really the study that is the title of the presentation, Transforming Our City's High-Performance Green Infrastructure. I encourage you to go to the WRF website, get more information about the project. At the end of the year, our final report is due. And all of the sites, with a couple of exceptions, all the detailed data will be included in that final report, and all the analysis of all the data we've collected. And you'll see it's quite voluminous, and this has been a labor of love for a number of years. But we also are working very closely with a number of universities. The University of Massachusetts is a collaborator on, and Casey Brown at the University of Massachusetts is a collaborator on the WRF research. But also North Carolina State, you'll see one of the sites I focus on quite a bit is at North Carolina State, Seattle University, UT, Austin, Mike Barrett has been working with us as well. But then a whole bunch of cities and private companies too. City of Austin, St. Louis, City of Chattanooga, Omaha, Nebraska, which Scott already talked about. Urban Drainage and Flood Control District, Ken McKenzie and Holly are here if you want to hear more about their projects. DDOE in Washington, D.C., St. Joe, Missouri. Let's see if I left anybody out. Oh, University of Chicago is a new site in Gwinnett County, Georgia. SAP Americas and Nestle as well. So, and then I would point out one other entity. If you haven't learned about Renew It yet, it's a NSF funded engineering research center at Berkeley, Stanford, Colorado School of Mines, and New Mexico State, and I really encourage you to look at their work. NSF is spending $40 million over the next 10 years through Renew It to broadly, and I think optimistically, reinvent the nation's urban water infrastructure. So that's what their mission is. So an outline for what I'm going to talk about. I'm going to give a little bit of background so that you understand the underlying concepts of the approach we're taking. It's a significant departure from the technical approaches for real-time monitoring and control as they've been done in the past. Talk about the details of those strategies. This presentation has many specific examples, lots of pretty pictures. I promise after about the first 10 slides, I've got lots of nice photographs and screen captures. And then give some actual data analysis results. We have, as I said, quite a few, but I'll give some examples, and then talk a little bit about what we think all of this means and what it could mean for all of us relative to the future of our practice and where we're really headed. So some of this perspective. So I'm going to mention the term the Internet of Things. How many of you have ever heard that term, except for if you've seen my presentation before? Only a couple of you. So I always say this, but in this room, probably, let's see, there's probably about 200 Internet of Things sensors right now, and they're all embedded in your cell phones. The accelerometers that tell you what the orientation of your phone is, the compasses that are in each of your phones, the GPS devices, they're all Internet of Things sensors, which means that they are things in the physical world which are directly connected to the virtual Internet. Right? So it's just a matter of software to take those things and use them in interesting ways. Like we could figure out, just looking at your accelerometers, which one of you has gotten up in the last 15 minutes to head to the restroom, right? Or has gone in and out of the room. It's really just, it's taking those sensors, and then by connecting them to the Internet, we can use them in new and novel ways. Another way to look at this is physical computing is another way to describe it. And it's not just me talking about it. This is a really pretty broad topic, and it's at the level where the National Intelligence Council put out, so this is an independent organization that assesses national security threats. The National Intelligence Council in 2008 put out a forward-looking report out to 2025, and they were asked to look at 6 technologies that they picked out with the potential to have significant disruption of our civil infrastructure, and that means kind of basically the fabric of society. One of them was the Internet of Things. And they identified a bunch of different scenarios that might play out between 2008 and 2025. And we are on probably their most aggressive track. You see this rapid adoption track. And if you read through that report, you'll see there are some concerning things. I think we all kind of know this about embedding these sensors into our daily lives and into our infrastructure. But there's also a lot of opportunities, and they identify those as well. And a lot of it has to do with how well, as a society, we embrace these ideas and protect our interests, certainly at a national level. And then if you're watching the Super Bowl, you'll see Cisco's got a commercial, right? And they're flying over a city, and they're going to tell you they're going to transform the world. There are a lot of these commercial smart cities, right? But their projection, when you look behind the scenes at the literature, IBM does the same thing. When you walk through an airport, right, they're telling you how they're going to control the world and make intelligent decisions. The projections by Cisco are that there will be 50 billion Internet of Things devices by 2020. And it's a stunning thing. It's probably a significant underestimate. This is a little bit old, and the numbers keep going up. So that's to say that most of the things I'm talking about are very important for us to understand, and frankly, these technologies have not been deployed to any extent of civil engineering before this research. So getting into the things that are really important to us as practitioners and as water resources engineers, I'm going to pose these few questions, and hopefully by the end of this discussion, we'll have some of the answers, or at least you'll have more questions to ask yourself about what I presented. But one of the fundamental things we approach this research with is asking the question. We've heard a lot of things at this conference about passive solutions, but the question that we asked is, can passive solutions solve problems in optimal ways given the the realities of the built environment? You all know the challenges that we have, especially in retrofit situations. Can we fundamentally rebuild our cities, or do we have other ways of fundamentally using the existing infrastructure in new and interesting ways? And then one level down, when you say, okay, maybe we should look at things besides just passive solutions, what roles can technology play in providing an alternative to that? And then understanding, hopefully from this presentation, where we are with the state of the practice and the state of technology. So I didn't just decide one day that this sounded like a really cool thing to go out and research and work on. It's like most things that look really interesting. They take a long time to develop. The very first opportunity in my career to look at this was a research study funded through SciSeat. And the goal of the project was really fundamentally to take information from the internet and get it out to control real things in the cheapest, most efficient way possible. And this was specific to salt marsh restoration. And that's a whole other presentation on its own. It was a really great project, but we got $250,000 basically to find the lowest cost, most efficient way of taking information and using it out in the environment. And at that time, so this project wrapped up around 2007. As you all know, I mean, how many of you have had smartphones in 2007? Okay, none of us. How many of you have them now, right? Fundamental change to the way we actually operate with information. This research, right as it was wrapping up, we were able to look at and see that there were fundamental new ways to do what we had done. We had used conventional industrial automation and SCADA equipment to do that work, and we realized things were really changing very quickly. So we learned a whole lot about that, and as a water resources engineer, I saw that there were lots of opportunities to do different things. So I'm going to mention this term, Scott mentioned OptiRTC. That's kind of our commercial name for what we're doing. But the underlying research is really highly distributed real-time control. And what is it really? It's an ecosystem of smart environmental infrastructure. And the key thing you'll see in the architecture that we have is that it's completely scalable. So you're not limited by the physical constraints between where sensors are, where actuators are, and the way in which you use them. And you'll see that based on the structure. We also are using a cloud-based platform, which means that we can go from having controls at a rain barrel size or to the scale of controlling literally hundreds of thousands or millions of devices in parallel. And the architecture is exactly identical. The resources can be scaled very easily, and that was one of our underlying goals. So Scott put this diagram up, and I know it's got a lot on it, but the Internet of Things really looks like this. You've got things out in the environment. In this case, for us, we're interested in things like pressure transducers or ultrasonic level sensors, rain gauges, and then, like as Scott showed with that great video, things like actuators, components of the infrastructure that we can install and then control. And what we do with an Internet of Things-based approach is right in the field, like at the end of these sensor wires, we turn those data streams into Internet-compliant data streams into Internet-compliant data streams. So with this physical device out in the field, this is at the North Carolina site that I'll talk about, we turn that data stream into a piece of information that looks like every other piece of information that's flowing around the Internet. The systems then that we use to interact with these, and this is in both directions, are standard enterprise data management systems. These are the same systems if you decided to go out and start an e-commerce company, or you wanted to run a bank, or you wanted to run an accounting system. You use a standard enterprise data management system. Historically, that's looked like something like SQL Server, where you buy a server, you install some database management software, you write an application to run on it, you run a whole bunch of hardware. But in the last few years, since we started this work and pursued this research, there have been a whole new class of these types of services, and they're all cloud-based. You hear that term a lot, but what does it really mean in this case? We're not just outsourcing hardware and using a server farm somewhere to take the place of our infrastructure. We're outsourcing the entire platform. So this is called Platform as a Service. And we use Microsoft Windows Azure. So like Xbox 360 is built on Microsoft Windows Azure, for example. But Azure is this stunningly large system. Just to give you an idea of the amount of storage available on it. And it's available for a price. I could log on and we could buy the storage. All of the data for everyone in the world for Facebook is about 100 petabytes of data, which is 10 to the 15th bytes. It's a lot of bytes. Azure has a capacity in excess of 300 petabytes. So it has a, as you can say, we're looking for something to scale, Azure scales. And the most important thing is we don't have to maintain any of the hardware. We don't maintain any of the bandwidth. We don't maintain the geographic distribution of the information. We don't buy any software licenses. Everything is basically rent as you go. You pay for this stuff at scale. So you can afford to do construction of these systems at very small scale, but then you can rapidly increase the scale of them to whatever you need. So the amazing thing is when you take real things like this and you turn them into what appear to just be virtual systems for enterprise data management system, is you can use any virtual piece of information that's also available in a similar format as part of the control logic of these systems. So the most important one that I'm going to point out is rainfall forecast information. Because the ability to know what's going to happen with green infrastructure systems fundamentally changes our ability to make those systems perform. And then the other really neat thing about just using standard enterprise data management systems to operate the environment, the built civil infrastructures, we can use everything that we use to interact with the Internet to interact with those systems. So web browsers, email, you want your rainwater harvesting system to tweet you or tweet the world when it's doing something interesting, or use a web service like voice auto dial. This is not some kind of custom proprietary software development task. These are web services that you just sign up for, and you send off your API calls out of your back-end system, and you get these services. They're all available to you. So that's by far my longest slide. I'm not going to get into the details of the differences in different cloud platforms or the underlying systems for the Azure application. We basically build a thin application. The way if you want to have an analogy, Azure is like getting Excel, and OptiRTC or DTRC systems are like building the spreadsheet, right? So people ask, okay, is it proprietary? And it's like, well, the Microsoft stuff is proprietary, but you've got to sit down and build it. It's like asking is a spreadsheet proprietary? Okay. Well, if you're the one who wrote the spreadsheet, you have a vested interest, and you obviously put it together. But the underlying approach is not proprietary. It's a standard approach. I'm going to show a whole bunch of examples around the country. I just wanted to point out we're actually using this for things that have nothing to do with water resources, like remediation systems. There's a landfill in Georgia that the entire leachate collection system is run in the exact same way as these water resources systems. And these are the kind of broad categories of example projects I'm going to talk about relative to water resources. I'm going to get into a bunch of detail on advanced rainwater harvesting, but also predictive retention and detention systems, controlled under drain bioretention, porous pavement. Scott already talked about that, so I'm going to skip it. And then active green roofs as well. Get closer. So the first one, advanced rainwater harvesting systems. So what's the difference between, why is it so advanced? It's what's the difference between a regular rainwater harvesting system and an advanced rainwater harvesting system? Well, the only difference, it's actually really simple. There's one valve, and Scott showed an example of that, but there's really just one valve that you're adding. And then you also need to know the level in the tank, the storage tank. But you take those two things, those are the only components you need, a valve to be able to drain the system and a level to know what the level in the system is. You take those two components and you connect them to everything I've just described. And you can do amazing things, specifically around forecasts, and I'll show the examples of this. So the project I'm going to highlight is our longest running pilot under the WRF research, and it's a collaboration with Bill Hunt and Kathy DeBusk at North Carolina State. They installed 3,300 gallons of retrofit rainwater harvesting at this site in New Bern, North Carolina. And then we did exactly what I've described to it. And what the system does, so at the cloud level, we ingest the quantitative precipitation forecast and the probability of precipitation forecast from NOAA. And this is what it looks like over a week. It actually changes every hour, so that's really complex to show, but this is essentially what it is over a week. And you can see there's, so this is predicted rainfall, and then the blue coming down is the probability of those particular components of the forecast occurring. So the system watches this every single minute, and NOAA updates it every hour, and it believes certain portions of the forecast. This algorithm is actually very simple. It only believes the components of the forecast that are greater than 70% probable, and we've had it running this way for a very long time. You can come up with whatever algorithm you want. This is what we started with, and I'll show you how effective it was. But this is what it looks like. So this is a web browser based. You don't need any software. You can have 1,000 people looking at this all at once. To look at these dashboards, you can just open it up in Internet Explorer. But this is what it looks like if you stand and watch this thing. It's a little like watching paint peel, but I logged on when this storm down here. So the site is right here off the north coast, on the coast of North Carolina. There's a storm almost over New Orleans. So this is about 24, almost 36 hours before a storm event. The tank was full. This upper left-hand graph, I'm going to show a bunch of these. The black line, if it's at the top, the tank is full. It's a 24-hour period. You can't see the dates. At 3 a.m., it saw that the probability of this rainfall occurring, this storm moving over North Carolina in the next 48 hours was highly probable. It said, I'm full. I'm going to overtop. How much do I need to drain down? The algorithm takes the forecast, the volumetric runoff coefficient, something we call the conservation factor, and it makes a prediction. It's gambling on the weather about how much storage it needs with the intent of getting complete wet weather capture. So this is the holy grail of rainwater harvesting, particularly in combined sewer areas. Complete wet weather capture, right? We're not running a model and seeing how many times it overtops. We're operating the system to achieve that goal, and it thinks on its own. So at 3 a.m., it made this decision up here to drain itself down during dry weather. The storm starts to move up the coast. The forecast hasn't changed. There were a couple of additional changes to the forecast. This one in the middle here, NOAA revised its forecast, increased the depth a little bit. It said, geez, it's still dry. I've got to react to that. It drained itself down a little bit. They revised their forecast back, but it said, I'm good. I've got enough storage. I don't need to do anything. And then the storm's moving up the coast. And that black line up in the top left can only go up when it's raining. So basically this system is not allowed to discharge during wet weather. It's made all of its bets, its algorithm is run, and it's got to wait and see how's it going to work out, right? So we're all holding our breath. This was actually the first major event we had after starting it up. The storms moved off, and here we are at the end of the event. We achieved complete wet weather capture, right? No discharge during wet weather, zero discharge, and we have more water than we started with in the rainwater harvesting system. This is an absolute home run. We were so excited when this occurred. And you're going to say, okay, you picked out a storm where you got lucky, and that's the case. We don't get lucky all the time. I mean, the algorithm got exactly right on that one I showed. This is actually from July, and this was a very long storm event. NOAA, when it was all over the place with their forecast, you can see the red line going up and down, right? The system made a bunch of corrections, and we ended up getting complete wet weather capture, but we didn't get all our water back because NOAA basically over-predicted the forecast. This was yesterday, the day before. The tank was nearly full, which is what it's supposed to do. And again, NOAA kept ratcheting the forecast up. They corrected it here. And then actually it didn't rain nearly as much. I just looked at it. It didn't rain nearly as much as we had anticipated. So we get it wrong sometimes, and I just downloaded this over lunch. So there's a storm coming, and it's not very probable that it's going to rain. So the system is not full because of that last event a couple of days ago. Like, it didn't rain as much as it was supposed to. And this storm is it's pretty shaky from the forecast perspective. So it's saying, you know what, I'm not going to make any decisions. NOAA doesn't know what's going to happen. I'm just going to wait and see. So we'll see. I mean, something will happen maybe later today. Black line will probably come up a little bit. And then I wanted to show you what it's like to interact with these systems. Let's see if we can do this. If you're North Carolina State or one of the other entities, this is the North Carolina State site. This is what it's like to go through the web browser and interact with these things. It's very dynamic. There's a mapping interface in addition to this querying strategy. So you have these sites all over the country. And like if you had a city and you had 1,000 rain tanks, or different pieces of infrastructure, you would have them all on it's like Google Earth for data, right? You can zoom into this stuff at a really extreme level of detail. So those are links to the dashboards. Interestingly, the physical reality of the user interface doesn't have to match up with the physical reality of the field. So like you're interacting with data doesn't have to have anything to do with what's actually going on. Like if you had 1,000 sites, you don't have to know where those are or what they are even to interact with them. And then this shows something that we think is super cool. It's called remote reality. Basically, when you bring up a remote reality interface, you'll see a bunch of them. You look at the image, it's like you're standing there and you have X-ray vision and you can actually see what the water level is. So what we do is we render every permutation of the possible field conditions, and then we map those to the sensors, and then we display that into the web browser, right? So you can be someone who knows nothing about this system. You don't have to know what gauges mean or even be able to read a graph. You can look at that like as the public and say, hey, I know what's in the tank. There it is. There's the level. So I'll show some more of those. And then I said we got lucky on that one event. I showed some where we didn't. The fact is this algorithm works really well. This is the period between August of 2011 and the end of the year, 2012. And we have full data going up to the present, too. I just don't have it on this graph. We had a period where it was offline in the middle here where you see some things. Anytime that line comes down, it's when it's made a decision or water has been used on site. Anytime it goes up, it's when it's filling. When it's at the top, it overtops. The bottom line is the system intentionally released 88,630 gallons making decisions during this period. They used 36,560 gallons in the rainwater harvesting system. And this is the result. We got an 86% reduction in volume and a 93% reduction in peak flow. And here's the comparison between if we had not had the intelligence on the system and made these decisions to open the valve up, and if we had it on, you'll see these two numbers are the ones I just talked about. But here's the comparison. If you just relied on the unreliable demand of the irrigation, you would have had 21% reduction in wet weather flow volume and 11% reduction in peak flow. 58% overflow frequency for the events compared to 18. And then the algorithm is very conservative about running out of water, and neither system ran out of water. But this is just taking a valve and a sensor and a really smart system and adding it to this significant investment and huge differences in performance. So there's a lot of talk about extreme events. I think a lot of the questions I've heard at this conference are about extreme events. Here's the system during Hurricane Sandy. So this is actually like, I was watching CNN, and I don't know, this is, I think it was, well, I don't know, it says 3 a.m. on the 29th, right? Dahlia knows what was happening in New York City at 3 a.m. that night. Not good. What was interesting is back on the 26th, this system saw Hurricane Sandy, or Superstorm Sandy coming. It drained itself all the way down. The university doesn't allow us to drain it below 900 gallons. That's to make sure that the gardener never gets no water. It was said it should have drained the whole thing, right? But during this entire period, from there all the way up to when it filled up, there was no discharge. And this didn't mitigate all of the effects, because it did overtop, and we could have used a lot more volume. But the point is, this tank was nearly full at the beginning of Sandy. This system worked as hard as it could to mitigate the effects. And this shows you the kinds of things we can do with our infrastructure relative to extreme events using information. Now I'm just going to go through a whole bunch of other examples of installations and types of installations. That one was in extreme detail. I'd say put your seatbelt on, because I've got lots of pictures and lots of different types. But it's kind of fun. The library in Austin, Texas, they had existing rainwater harvesting tanks. We added a valve in, level sensor. Here's the remote reality interface for that. Like it's better than being there. You can actually tell how much water's in the thing. We added bioretention. This isn't a combined area, so when it discharges, it goes to bioretention. They have a dashboard. This now has a remote reality interface on it too. In Washington, D.C., I like to say stimulus money didn't go very far. It actually went like, there's the Capitol, right over there, to a firehouse where we installed these above-ground tanks you see here on an oblique image. This is what they look like in renderings before we built them. Here's the remote reality interface. We put a virtual staff gauge in, so if you want to read it, you can. There's a cool video out at our booth where it shows the water going up and down. There's right after they were installed, above ground tanks. You put green roofs on top of them. This is, I was out there a couple of weeks ago. There's a couple of weeds in it, but they look kind of cool. They didn't plant the green screens yet. There's me looking pretty proud of the water coming out, but it's at a firehouse, so they use water quite a bit, but we can monitor their daily use. It works just like the ones in New Bern. We did it at another firehouse over in Anacostia. You see, this is the exact same design. The intent was to come up with a modular above-ground tank that could be installed anywhere in the district. The bargain is two of these tanks, they're perfect cubes, 7 feet on a side, fit in one parking space. So the bargain is you can get 1.4 inches of storage if you're willing to give up one parking space for 3,000 square feet of roof. Really easy calculation to make. In St. Louis, we built 7 projects in public housing areas. We call these rain gardens, or I do, because what we did was we took landscaped islands and we retrofit them with, this has 15,000 gallons of storage in a landscaped island. Polyethylene tanks, not above ground, not below ground. That's a really interesting story, but nonetheless, an interesting outcome as well. School in Denver. Let's give some of the details of what some of the components look like. This one's is wireless. There's a valve and the sensor. Those are like the key components. In Chattanooga, we installed a much larger system, an 8-inch valve. Operates the same way that Scott described, but this is for an underground harvesting system. One thing I'll say that I don't think anyone's really talked about at this conference, but is really interesting. Pipes leak like sieves. Most of our modeling, we don't assume this occurs. This system actually doesn't hold water. And that wasn't our design, but it's really interesting because they did all these green retrofits, and they found out that their rainwater harvesting system doesn't hold water because it all infiltrates in the pipe. So that's still an issue waiting to be resolved. Similar system this is a peak flow tank, no harvesting, just smart detention at University of Seattle. We just started on the contract to retrofit EPA headquarters. They have 6,000 gallons in the basement, and this is the rendering for their remote reality interface. This one's kind of cool because every tank has a different level, so it's a more complicated one. But we're retrofitting this. It should be done by the first of the year. And they only use it for irrigation there, so there's basically 9 months of the year where it does nothing right now, the investment. So we're really excited to have this thing work all year long, especially at EPA headquarters. One of the really big opportunities, you can do this exact same thing, not just with rainwater harvesting systems. How many flood control, detention, and historical basins do we have in the United States? And how much is it to retrofit them to improve water quality? Okay, this is a pond, a dry pond in Pflugerville, Texas. Completely off grid. It's all solar, all cellular. It's connected up to everything we just talked about. We basically turned the outlet design of this system into a software problem. You want it to be a dry pond, a wet pond, an extended detention wet pond. You want to change the permanent pool volume. All of those things are just settings in the software. So when you do this, here's an actual event that Mike Barrett operated. And you get really cool things. I mean, one thing that Scott didn't talk about, but embedded in this minute-by-minute data is an amazing amount of information about how these systems work. The slope of that line while the valve is closed, that's where it's going up, tells you exactly what the infiltration rate is through the bottom of this detention pond. We don't have that kind of data. As we start to instrument these systems, the monitoring data comes along because you have to monitor them in order to control them. So here's an example. This is a model of a year using SWIM, taking an extended detention pond, extended detention wetland, and all we did was actuate the orifice based on forecast information. And the bottom line is we're able to nearly double the residence time just by, instead of using the volume for these really short periods of time right after rainfall, using the entire volume and then draining it down before the rainfall, completely turning the hydraulics on its head. We're doing this at the Brooklyn Botanical Gardens. They're doing a $19 million upgrade of the gardens. We've taken their water features, and we're going to operate in this same way. When there's a high probability of rainfall, the water features drain themselves down, intending to get complete wet weather capture in a combined sewer area. Same thing with bioretention, just like Scott described for porous pavement. Retrofitting the underdrains of a bioretention cell, there's a big debate about, you might have heard Andy Reese's talk, which I didn't get to hear, but should we do retain on site? Should we do flow through? Should we have sumps in our bioretention cells? I mean, how much hand-wringing is there, right? I mean, you've probably heard this 10 times today. This, to us, is a software problem, right? You can change that on an event-by-event basis. You want a 12-inch sump? We'll give you a 12-inch sump. You want it to change from 12 to 24, depending on the size of the event? That's just a software and algorithm issue. You want it to be flow-through for large events and then close during the peak period when there's a combined sewer issue? It's all doable. All you got to do is just decide when you're going to open and close the underdrain. And that's kind of the concept of what they look like. The first one has been installed in Gwinnett County, Georgia, and it was actually just installed last week. And the last one I'll bring up, this one is a completely different application, but it's all the same hardware. We've got an ultrasonic level sensor and a little wet well. This is a beautiful turf grass flood irrigated green roof at SAP headquarters outside Philadelphia. And there's two components. There's a level sensor and a solenoid that opens water to irrigate the grass. Really simple. Actually, this replaced a $2,000 mechanical float valve, which I think was asked earlier. And this is what it does. So this is from July. During the day, every time this little line goes up here, it's basically irrigating. It's keeping the flood irrigated level between 1.37 inches and 1.57 inches. And we watch in extreme detail. We probably have the best ET data set on a turfgrass green roof anywhere, because we know minute by minute exactly how much water is being taken up. And then, so once you do this, the really cool thing is, okay, so we replaced a float switch. We also can just make the decision based on the forecast to not irrigate. So we can depress the flood irrigation layer, gamble on the weather. The cool thing here is if you get it wrong, you just fill it back up, right? So you save water, and you get stormwater benefits by just taking a dumb mechanical system and basically changing it to an electrical mechanical system, and then most importantly, connecting that up to this infrastructure. It fundamentally changes how you can operate these things. And I think I did, so this was a storm event from July. Yeah, this was yesterday. So the 18th, you can see the storms moving up. Actually, again, remember I showed from North Carolina, it wasn't very probable that rainfall that was moving up the coast was going to occur. So same thing was seen in Philadelphia. This blue line up here would have come down, which is the goal if the rainfall had been highly probable in Philadelphia. It actually did. The reason it didn't keep like jogging up and down is because it started to drizzle, right? So it was kind of improbable, and it started to drizzle. So the system said, you know, I'm not going to deplete the flood irrigated layer because I'm not really sure about this. But it did rain a little bit, and it stopped watering, but we didn't really get a big stormwater benefit. And then I just wanted to mention, so the sensors don't have to be limited to just level and flow, the things that are really easy to monitor. These are 6 water quality multi-parameter probes monitoring a dam reconstruction for the Corps of Engineers in Tennessee. And this was downloaded yesterday too. So we just used a standard multi-parameter probe. We feed all the data in. The point is, you can use this exact same information to do everything else we've talked about before. And it's just about up to us to come up with the algorithms to control these systems in ways that are beneficial to the environment. And then closing thought. So as you can see, for me, it's really hard to overstate the importance of the integration of information into our existing infrastructure and into new design and construction. We're at the bleeding edge on this stuff in research. There are 1,000 dissertations to be written on this, and I anticipate they will be. One thing that I see in getting really close to managing data in this way is that it's really the biggest fundamental change will be in our ability to actually monitor things, right? So this is about sensor technologies, and the advances in sensor technologies are progressing very, very quickly. And there's a whole bunch of reasons for that I don't have time to get into. But we are headed to a world where for literally dollars, you're going to be able to collect things that cost thousands right now. Accurate turbidity measurement, accurate nitrate, phosphorus, even things like there's some great companies working on probes that are specific to constituents that are very important to remediation, like TCE. It's a company in Colorado that's developing TCE probes that we're working with. These things, and they will come about, will fundamentally change every one of our jobs. It will fundamentally change the regulatory structures that we even operate in. So like take the Chesapeake Bay, for example. How much time has been spent on arguing over the model for the TMDL in the Chesapeake Bay relative to nitrogen, right? Imagine a world where you don't have to guess what's happening. You actually know because you have the ability at a reasonable cost to monitor what's actually going on in the watersheds, at each individual outfall, in the receiving waters. Our biggest problem is a problem we are already having on this project is the quantity of data. Petabytes of data are going to be coming back from these systems. And our jobs are going to look a lot more like big data than they are about running spreadsheets 20 years from now. If not entirely, that's what we're doing. I think empirical analysis will supplant modeling to a great degree. So, and enhance it, frankly. I mean, how many of you would have uncalibrated models you put together, right? Okay, everybody who's done any modeling has put uncalibrated models together. Our challenge is going to be the fact that we are able to calibrate those and the massive amount of data. I mean, even just what Scott showed for a porous pavement parking lot in Omaha, he literally has hundreds of thousands of data points with which to work. So it's a very different thing. And then, if nothing else, what this has taught me, all this work, is that there are an amazing number of opportunities. There's an incredible amount of new things to do in our field, and take some risks. You know, like go out on a limb, and there's a lot to be done. There's a lot to be done that isn't just to worry about the fact that we don't have enough money to do it. There's a lot of things that we haven't even come close to optimizing, and I think our jobs are going to look a lot like optimizing investment and our existing investments more so than doing completely new things and reinventing everything. So thank you, and I appreciate the time. Sure. Yeah.
We have time for a couple questions from Marcus, also for Brad and Jim if you have questions for them.